Thanks, Chris. So I'm going to talk about the Data Central Science Platform and really from a broad uh, sense what a science platform is for, and it's to bring all the data together and derive new science. Um, what this talk aims to achieve is really to give an overview of the virtual observatory and how it supports accessing all these data, the tools that you use that are usually or very often built upon the virtual observatory, and what to do when you can't download all the data. So you saw in Sven's talk, his examples involved downloading the data to your laptop, which if you're dealing with a handful of spectra or even a few hundred spectra, that's not a problem. But if you want to manage many thousands of spectra or even hundreds of thousands or millions of spectra. So I'm thinking, Foremost and these kinds of surveys or survey instruments, then you need to be able to do something. And that's where the science platform comes in. And I'm going to give a very, very simple example of how you can bring X-ray, radio, and optical together. But then it's just really to lead into what is possible. And just a big, very large caveat, this talk cannot possibly cover everything there is to know here. This is a very huge field. We have annual conferences devoted to this kind of thing. So the virtual observatory and FAIR data, and I'll describe what I mean by FAIR data. The virtual observatory at its highest level is a vision at an international level of standardized ways to find, share, access, and interpret astronomical data. So it's driven by the International Virtual Observatory Alliance, which was founded in 2002, and Australia and Germany are both founding members. The IVOA developed standards and protocols that are then implemented by observatories, data centers, and other holders of data. And you've already seen examples from Chris Onken looking at the TAP service, which is one of these standards, and ADQL, we've heard a little bit about that as well. ADQL is an IVOA standard. And these standards have significant overlap with the FAIR principles. So these are very, very simply, there's a Nature paper here that's linked, and so these slides will be available, but they're basically that data should be findable, accessible, interoperable, and reusable. So when we're talking about findable here, we're really talking about how easily can your data be discovered. If I go to TopCat, for example, what data can I find? And there's a big registry of services and ranging from TAP services and cone search services and image services there. And you can go and run queries and download and visualize data. And you can do this programmatically as well. You don't just have to use TopCat. Accessible, so how easily can your data be obtained? Is it public access? Is it something that you have good data formats for? Obviously in astronomy, we primarily use FITS, but you'll find that in some data sets, they may be in a different format, such as HDF5 or everyone's favorite CSV, but there are even variations of CSV files. So interoperable here really means how easily can your data be compared? So if I go and query the SkyMapper TAP service, I can run a query there and then run it on the Data Central TAP service and get very, very similar formatted results. So then I can do a much easier comparison of the data sets. And then finally, reusable, which is how easily can your data be trusted? And this is something that within astronomy, we don't really talk about very much. We don't really deal with very much, but it's really fundamentally about licensing. It's not just about the data quality and data integrity, although that's a key part of it, but it is really about data licensing and who should be able to access your data. So the virtual observatory is very, very fair, and in fact, we had a paper a few years ago that found that basically the VO standards are if you fully implement them, then there's only two things to meet this sort of external cross-disciplinary definition for FAIR, and that is to add a license, as I mentioned, and then to have a digital object identifier, and that's usually it's a persistent identifier. You would have seen it for papers definitely all of the journal articles that you've ever read and a lot of things in archive will have a DOI, but data is also increasingly, and software libraries are increasingly having digital object identifiers attached to them. So this brings me to the Australian All-Sky Virtual Observatory, because that's what I'm most familiar with. There is a German Astrophysical Observatory as well, GAVO, but I won't be talking about that today. So the Australian All-Sky Virtual Observatory is the sort of the representative within the IVOA community. It's supported by AL, and they select a representative to sit on its executive. That executive is currently me. The ASVO has 5 nodes, so it's a distributed data model, and we coordinate much of the data management and services. SkyMapper is in fact one of those ASVO nodes. The NWA that provide data sets like Gleam, GleamX, Lobes, and various others has a node. Theoretical Astrophysical Observatory, or TAO, which is a cosmological simulations system. They are also part of the ASVO. CASDA, which includes the ASCAP archive, so data sets such as EMU and Wallaby. Well, particularly the raw data and the processed images, but not so much the high-level science products, and Data Central. And we include the Anglo-Australian Telescope Archive, soon to be the 2.3-meter telescope archive, and many other data sets, particularly the high-level science products. And I'll talk a little bit about those in a moment. So the VO services that we have a table access protocol, which is commonly known as TAP, and ADQL queries can be run against that. We saw Chris give an example of that. A simple cone search to find your favorite objects, simple image access to query multi-wavelength images. Basically, you give it a coordinate and a radius, or it is a radius, not a box, but and then you can find whatever images are in that field, and similarly for spectra. There's a service for that. So the simple cone search, I won't go into a lot of detail here, but basically it's built on just basic web requests, so HTTP requests. It is returned in a specific virtual observatory format called VO table, which is an XML format, but you don't really need to know much about that because you can handle that through AstroPy, for example. In astropy.io, there's a VO table package that can handle this seamlessly, and you don't have to worry about the vagaries of XML. But that will include the metadata and all the information that you might need about the data. And management of all of these services is made much easier using TopCat or the PyVO library. Similarly, simple image access, these are all very similar. They're basically a cone search, but returning either a set of IDs and distances, or a set of images, or a set of spectra. So the table access protocol is a little bit different. You saw, as I said before, Chris Onken gave an example of queries that you might run on SkyMapper. Data Central does have a TAP service as well. You run your queries in ADQL, and the results once again are returned in VO table. But as a user, you don't need to know that really, because TopCat or PyVO or AstroPy handles all of that, or AstroQuery handles all of that for you. But it gives you all of the metadata of the query. It gives you the results of the query, and you can run the queries synchronously or asynchronously. And so the latter is very valuable if your queries are very long running. You don't want to have to wait for them to return. You can just run the query, and it will return when it's ready. I have a notebook that I'll provide everyone later, and that has an example of such a query. And once again, TopCat and PyVO or your other favorite similar libraries can handle this kind of service. ADQL, here is an example cone search that you might do with ADQL. So ADQL is an extension of standard SQL, structured query language, and it basically allows spherical geometry and celestial coordinates and reference frames to be considered, so that you can index across coordinates such as right ascension and declination. As Chris mentioned earlier, it only accepts ICRS coordinate systems, so just bear that in mind. So you'll see a lot of things in degrees and not arc seconds or arc minutes as you might be more familiar with. But it allows you to do a lot. That's just a simple Gaia DR3 query. I recommend you have a look at the short course on ADQL put together by the German Astrophysical Virtual Observatory. It's a fabulous resource if you want to really get into some of these more complex queries. And then I provide some other references for SQL and how to write ADQL queries for Gaia data, and then a cookbook as well. So please have a look at these later. As I said, this is such a big field, I don't have time to go into all of the details. And there's some fair references as well, and how the AstroPi and the Virtual Observatory have very strong connections. So accessing data, this is what we're really here to try and understand. How do I get all of the data that we've been hearing about? Well, there are multiple ways you can do that. You can access it or you can download it. You can query using the VO services that I mentioned. That could be a programmatic way, an application like Topcat. You might go into a web portal similar to the SkyMapper one, or you might go to a science platform, which is usually, it has a web component. It might have notebook type systems. It might have all sorts of other services that you can use. And you can program it, access data programmatically using a bespoke API. So for example, I think it's the legacy survey, which comes out of NILAB. It has a bespoke API. So you have to go and learn the particular commands to query and download data. So eventually you'll need to interact with a database in some way. So it's definitely worth having a look at ADQL because that allows you to do a lot more complicated joins and cross-matching than you might otherwise be able to do. So the standalone applications, obviously Topcat, we've heard a little bit about already. Stilts, which is very much a set of command line tools that sits underneath Topcat actually. So it's a series of command line tools that you can do cross-matching, you can process tabular data, you can do all sorts of transformations with Stilts. There's no Python library. This is a Java application, so you have to run it on the command line. Aladdin, of course, a lot of people would be familiar with Aladdin. It does actually, it's in large part dealing with images and catalogs, but it actually has got some VO services under the hood as well. And then DS9 is a long time favorite. It's been around for 40 years, and it can deal with a lot of imaging and data visualization, particularly of FITS files, and you can do some sophisticated overlays and blinking. Particularly, I think Chris showed an asteroid moving through a field. You can do that kind of blinking with DS9. But I won't. These are just these are linked here, so I won't go into much more detail. Science platforms. So in Australia, you can find a lot of these significant data sets, and Chris Wolf showed them at the beginning, a lot of data sets that are part of the eROSITA AAL collaboration. So we've got a lot of radio and optical and infrared data sets here, and all of these can be found in Data Central, actually. So in some ways, many of them are, so we've got multi-wavelength and some simulation data as well, and they provide access, and you can access data sets all around the world. And we use, built on IVA tools, we use a lot of AstroPi, Jupyter notebooks. We do run RStudio and Shiny apps as well, and PyCPL is an ESO data reduction package, which is not really important here, but RStudio is something that there is a subset of the community that write a lot in R. It's not just Python, and in fact, a Jupyter notebook can handle that because the Jupyter actually refers to 3 different languages that it's founded upon, which is Julia, Python, and R. So, which is something I actually only learned recently. So this is Data Central. I will give a little bit of an overview of the notebook system in a little while, but a science platform is really it's usually the notebook systems and maybe some other kind of compute services. They could be a remote desktop. It could be data processing or reduction pipelines. We provide services to reduce large-scale ESO data, for example. And the benefit here is that you get a sandbox environment. You can run your code on your data, but using external resources. So this is something that we're very keen to expand, because we've got a lot of data that you can access. And a lot of it, I think Chris Wolf mentioned it earlier, there's a lot of public data, of course, and increasingly there's a lot of proprietary data as well. And we will be hosting the Australian LSST International Data Access Centre, and that will be integrated into Data Central, but that will be proprietary in the first instance for people with Australian access. And potentially, if you are in Germany and you have access to LSST data, then you could potentially access it through our system as well. So some notable science platforms, I mentioned Data Central. CANFAR in Canada is a very large one, very long-standing. It's the Canadian Astrophysical Data Centre. They've been operating for around about 40 years, but in the last, say, 15 years or so have really ramped up in terms of their services and compute and data platform and science platforms. And then there's the Rubin Science Platform for LSST data. So some of the data sets that are relevant to the eROSITA collaboration are listed here. So in the gray, we've got the Gamma, the Galaxy and Mass Assembly survey. Devils, the data release one is basically in there, but it hasn't really been announced yet. OzDes, which is a supernova survey, 2DF Lens, the Semi-Galaxy survey, Galar that Sven talked about. And so all of the services that I talked about before, all of the querying tools, so you can actually run the queries on our infrastructure and not have to download all of the catalogs and data. And that allows the extra cross-matching. So then there's the 60F Galaxy survey that Chris Wolf mentioned. S7, we host some data. I was really happy to hear that there's been more data since the Adam Thomas paper of 2017. We also have the GleamX radio data, so we're sort of bridging into tomorrow's set of talks. Deeper, wider, faster. We're in the process of, we're working with the Deeper, wider, faster team, which is the transient survey team, to bring their data release, their first data release into Data Central. That will be coming in the next couple of months. Then we've also been working with the EMU team to look at some of their data needs, working in collaboration and partnership with the Australian SKA Regional Centre. And that also then leads to the Wallaby survey, which is another ASCAP survey. And then finally, the last two there, the WAVES survey, and I should in fact also included the 4HS survey, which is another foremost extragalactic survey. But we're working with these teams, and those data products from those surveys will be within Data Central, will be released through Data Central. And then, of course, the Hector Galaxy survey as well, which is one of the large AAT surveys currently running. Their data release will be coming in, I don't know the time frame, but it will come through Data Central. So now I'm going to give a very brief example. This example uses eROSITA data release 1 because that's what I could easily access, but you can in fact replace it with proprietary data as well. So the kind of queries that I'm talking about should work in any JupyterLab type system, as long as you have the right sort of AstroPi and various other packages installed, but that will be clear at the top. The notebook you can get from that QR code or that link. And there are also other Data Central examples found at that link there. So I'm going to stop this share and move to a different share. Which I think I want to keep that one. And then jump to here. And go all the way to the top. So this is a very basic tutorial these are the kind of Python libraries that you need to consider and have installed. So really it's AstroPy, PyVO, Pandas, a lot of standard things. I'm not going to go through all of this tutorial here, but I will just sort of highlight a few things. So we can the AstroPy uses something called has a SkyCoord object, and you can basically set it up. And these are the kind of things that you can put into your various queries using PyVO and other AstroPy services. Just a lot of setup here, setting up URLs to find all of the data. A simple cone search here. So this one is actually just a code search within Data Central, and you see it just returns a whole lot of objects, some in Gleam, some in 2MASS, some in the 2DF Galaxy Redshift survey. So 154 objects. You can display it in all sorts of nicer ways using pandas, etc. And so I will just skip on ahead here to the cross-matching. And so here we have a thing where we can basically, we set up this is the simple cone search virtual observatory compliance service for eROSITA for data release 1. You can run your query. You basically just go and do a cone search using the PyVO data access layer library, and then you need to just put it into this SkyCoord format so that you can then do some really simple cross matching. Basically, that's what we do here. The cross matching, it's just this match to catalog on the Sky method from the SkyCoord object. That will just give you a list of here. Basically, you put in your eROSITA table, and then you find all of the things in Data Central that match that at the same position. It's quite a large position. I think it was a degree radius. And then these are the coordinates of that. So that's not particularly useful, but there's the coordinates, and then you also get the angular distance on the Sky from that from the central coordinate that you put in. But really, what would be more interesting would be to see the actual objects and what data release they're from. So these, basically what you see here is a list of all of the 135 objects that have an X-ray, an eROSITA X-ray flux. So a lot of them are in the 2DF Galaxy Redshift survey, quite a lot in 2MASS, some in Gleam. So, just a really, really simple example. And just later on, if for those who are interested, you can see that we can get GleamX imaging and visualize the imaging as well in whatever formats you want. And then there are different ways to get spectra as well, and all of the spectral results. I don't want to go into that in a lot of detail, but I do encourage you to have a look, and then visualizing this is a gamma spectrum. So now I'm going to skip just very briefly just to show TopCat because I realize we're running a bit short on time. So this is the Data Central TAP service. As you can see, there's a lot of data in here. There's Devil's DR1, there it is. All the data releases for Galar that Sven talked about. There's also another Galar data release that matches the a field observed by the TESS satellite. So time series photometry there. Lots of gamma data, Gleam, MWA data. Lobes is also an MWA survey. OSDES, S5, SAMI, Wiggles. There's a whole lot of data sets that are available in the TAP service that can be queried. So I think I might stop there because I realize I'm running a bit short on time.